3. Hi, I'm Colton Story, and this is Kyle Shipman, and today we're going to talk about our senior project, which was the Wart Eliminator concept. Alright, first I'm going to talk about the agenda for this presentation. First I'm going to talk about the background regarding this product, just tell you a little bit about it and give you an idea on the concept. Next I'm going to go over the problem statement. I'm going to explain to you what the problem was at the start of the project and what was exactly needed to overcome this. Next, we're going to go over the methodology, which is we're going to go over the steps of how we went about our project from the beginning to the final deliverables. Next, we're going to go over the new design and show you the new design that we came up for after in-depth evaluation. Next, we're going to go over a cost analysis, which is we're going to give you a rough estimated fully allocated cost number and how we estimated this value. And last, we're going to talk about the product impact on the future and how this product can be helpful once put into production. So first, I'm going to talk about the background regarding this device. The concept behind it is that it's a home medical device. It's derived from the concept of resonant frequency. So for example, we've all heard of the concept of the harmonic frequency hitting a wine glass and causing it to shatter. In this case, it is shattering a pathogen. So matching the frequency of that pathogen will cause it to devitalize and therefore die. And in this case, it is the Wart virus. So what this product does is it runs a 21.27 kilohertz frequency through the body at two different power levels chosen by the user of 5 volts or 15 volts for 3-minute cycles. Now, how this works is you grab the device with one hand and the probe with the other and apply the probe to the affected area, and then it runs a 3-minute cycle while maintaining this frequency. So next is the problem statement and the scope. So when we first got this product, it was still at the prototype stage, and what this concept needed was to be taken to the next level so that it could be at one point produced large scale. Now for the scope of our project, whether or not that this product works is not in the scope of our project, and further testing is needed in order to actually prove that it actually works. At this point, all that there is just a theory behind it.
So the first step we took in figuring out what we could do to take the Wart Eliminator to the next level was give an online survey to 100 participants regarding features of the product. Upon receiving the survey, the subject read about what the Wart Eliminator does and how it worked. Then they were asked to rate 7 different categories from not important to very important. Our results showed that the main features that we would need to be focusing on were the ease of use, training material, price, size and feel, and quality, as shown by this graph. Because size and feel were a big issue in our survey, we decided to run a 2-factor design of experiments testing comfort ratings of subjects holding 2 different mold shapes with both their right and left hands. Since the original design was meant to be held in the left hand of a user, we wanted to compare comfort ratings with the mold that was designed to be symmetrical and work well in both hands. To start the test, 50 men and 50 women were randomly selected and read a script that told them to grab either of our molds with a specified hand. After this, they were asked to rate their feeling of comfort from 1 to 10. After testing, a 2-way ANOVA test was then used to analyze results. In conclusion, it was found that there was a significant difference in comfort ratings between left and right hands and between the 2 products. With interaction, however, we can say that a certain product may play a larger role in the difference in comfort levels between different hands, that being the one of the product meant just for the left hand. With this, and in addition with the comments from test subjects, we are confident that a product that not only is symmetrical like the square design, but is curved on both sides is the best option for a new product design. Here's our null and alternative hypotheses with our p-value results for the test. This new design looks like this, with two curved sides that can conform to both hands equally. Though this may have seemed like a very simple solution, the change was quantified and justified by the design of experiments. With the new design in place, we wanted to create the beginnings of a user manual for the Wart Eliminator to tackle the ease of use and training material parts to the survey. This included a startup guide describing how to get the Wart Eliminator up and running, a features diagram labeling all parts important on the product, and a step-by-step operation instructions with all necessary notes and warnings. Below are some example figures used in the operation instructions.
So next, I'm going to discuss the cost analysis that we did based on 1,000 units of production. So this cost analysis is a fully allocated cost based on labor, material, and overhead. First, for the total labor cost, this was calculated from information from Premier Plastic Resins Corporation. First, at a shop rate of $75 for setup, for the injection molder, this is calculated to take 2 to 4 hours and comes out to 15 cents per unit. Next, for machine runtime at $30 an hour at a 36-second average cycle time at 100 units an hour, with an operator cost of $15 an hour for 10 hours, this comes out to 45 cents per unit for the 1,000 units of production. Next, there's the cost of the mold. For the injection molder, to make the exterior shell, which comes out to $60 an hour at 100 hours for a total of $6,000 or $6 a unit. Next is the assembly on the manufacturing floor, with a cycle time estimated at 30 minutes per unit with 4 operators at $15 an hour, coming out to a total of $3 per unit. Next is the cost of material. Total parts for the printed circuit board derived from Infinetics Corporation, who first made the initial PCB prototype, comes out to $10.49 per unit, while the outer shell, probe, excess epoxies, tools, machines, etc. are all estimated at $6.27 per unit. This is a rough estimation. Next is the overhead cost. This calculation is very difficult and hard to know because, first of all, this product has not yet been put into production and there is no facility, so it is not possible to know the rent, insurance type, how many supervisors, cost of machinery required to have these products produced. So the rough estimate given was $10 a unit, but further estimation in the future is required to get a more solid number for this specific cost. But the total fully allocated cost that we calculated based on all 3 of these areas was $37.76 per unit. Now last, the impact that this product could have on the future could be very significant. It could be a product available at a cheap price for everyone, and it could be a potentially solution for ridding patients of common warts and even the more severe cases such as HPV. Our work in this project leads to more production possibilities for this product to be implemented large scale into the future. Thank you.